Hey Professor, this is Rob Hines. This is my video submission for our first project in this class. All right, so before we get into my actual code and all of that and my contour plot and that kind of stuff, I wanted to just regurgitate the, project, the problem statement, and all of the project entails. So
we have our first project. This is our design project. And it's the MATLAB-based design of a cantilever beam under load. So the objective for this project was basically to design a cantilever beam that's subject to a point load at its free end. And we are required to develop a MATLAB script that models the beam, analyzes its stress and deflection, and optimizes its cross-sectional dimensions to minimize the weight, all while ensuring that it meets the specified constraints on maximum stress as well as deflection. So after the objective, you got the problem statement. We're tasked with designing a cantilever beam that will support load P at its free end. The beam is made from a material with a known yield strength and Young's modulus E. These are just variables for Young's modulus and the yield strength. And the objective is to minimize the beam's weight by optimizing its cross-sectional dimensions. And in doing that, we needed to ensure that the maximum stress in the beam doesn't exceed the material's yield strength. We needed to make sure that the max stress in the beam does not exceed the critical buckling stress. Then we also needed to make sure that the deflection at the free end of the beam did not exceed a specified limit of this variable right here. Then they gave us data to work with. They gave us the length of the beam, the applied load, material yield strength, Young's modulus, maximum allowable deflection, and density of the material that we're working with. As far as the cross-sectional shape is concerned, the beam is a rectangular cross-section with a width of B and a height of H. I low-key thought this was a little bit weird instead of just using X and Y, but it's fine. These dimensions can vary along the length of the beam, but for simplicity, we assume that they're constant. And then we've got the mathematical model section here. We've got the stress calculation, max bending stress, the fixed end of the beam. This is the formula for the max bending stress. For the maximum bending moment at the fixed end, we have this. C is the distance of the neutral axis, and then I is the moment of inertia. And then you have their respective formulas. We can substitute these into this stress equation right here, and this equation, or to ensure the beam does not yield, we want the max bending stress to be less than I think that's the yield. Yeah, the material's yield strength, just to ensure that the beam does not yield. Then to ensure the beam does not buckle, we want to make sure we meet this constraint, and these are just basically constraints that we want to abide by in this project. You've got the deflection calculation, you got the max deflection at the free end, it's given by this right here. Substituting the moment of inertia, we get this. Then we want to make sure that the deflection does not exceed the allowable limit. We have our weight calculation. This is weight calculation right here. V is the volume. G is acceleration of gravity, 9.81 meters per second squared. The optimization objective, we want to minimize the weight W by finding the optimal values of B and H. I think that's the length to height again, while satisfying the two stress constraints, as we just looked at here, and the one deflection constraint. So of course we're told to make a MATLAB script that meets all of these. And then for the submission requirement, this video has to be 10 minutes. We got different criteria, etc. So now that we've went over that, we're gonna go ahead, get into our code and our contour plot right here. So this is the code. And I'm going to explain the code first. Then I'll explain the contour plot and why that is significant. And then I'll just summarize what all we've covered here. All right, so we got the first line of code. This is just clearing everything out, includes a command window, removes all the variables, closes all that. Okay, then this section right here, basically what this does is it defines the parameters that we were given in the problem, such as beam length, the load, the material properties, and the constraints as well. Okay, so these right here, this is just the range, or the B range, and then the H range. Basically, what these two lines do is they create a range of values for both B and H. And in this specific case, we wanted them to vary from 0.01 meters to 0.1 meters, and then we wanted 100 steps. Basically, this defines the search space for the optimization. And then this line of code, line 13, basically what this does, it just makes a grid for the values with B being the width again and H being the height, and it evaluates the equations at all possible points. So that's basically what that does. Okay, line 15. Basically what this does is it just calculates the moment of inertia for each pair of B and H, each pair of the width and each pair of the height. All right, and then basically what line 17 and 18 do is it just computes the bending stress. Then once again, one of the constraints for this project was that the stress must not exceed the yield strength. So that's what line 17 and 18 do. And then we have line 20 right here. Basically what line 20 did is calculates the max deflection. And what it does is it computes the beam deflection at the free end. Then I think one of the constraints was we wanted it to be less than 5 millimeters. So that's line 20. And then what line 22 does is it just it calculates the beam weight. And it just computes the beam's weight by calculating its volume and multiplying it by the density and gravity. Basically what lines 24 and 25 do, they basically create logical matrices based on true or false. Stress constraint, line 24, what this does is true when stress is less than or equal to the yield strength. And then line 25, the deflection constraint, is true when the deflection is less than or equal to the allowable deflection. All right, moving on from this section, lines 1 to 25, we get to lines 27 and beyond. What this whole second half is doing is it's helping us create our contour plot. All right, so lines 27 through 29, it basically just creates a field contour plot with a beam weight. All right, switch it around a little bit so it's easier to see, but we have lines 31 through 34. Basically, this gives us a red line. What the red line represents is it represents where the stress exceeds the limit. Then we have a blue line, and the blue line just shows where the deflection exceeds the limit. Deflection, not stress, for the blue line, and then stress for the red line. And then the green line basically displays the region where both constraints are satisfied. And then the last segment that we really need to focus on is lines 36 to 41. Basically what this is doing is just, you have the labels, the legend, and the color bar, and this is just basically all just for better visualization for the contour plot. So more or less, that's the entirety of the code, what the code does. And now I'm going to go ahead and explain what the contour plot does and why it's significant. All right, so this is our contour plot when we take a closer look at it, or when we stretch it out. So basically with the contour line, we got a couple lines here. Or the contour plot, we have a couple lines here. So first and foremost, you see this red line. Basically this red line, it represents the stress constraint. So any area above or to the right of this red line, in this area right here, basically this exceeds the material's yield strength. And this just means the beam would fail because of the excessive bending stress. In addition to this red line, we can zoom in a little bit. Hopefully that doesn't mess it up. Okay, that's fine. So we also have this blue line here. What the blue line does is it represents the deflection constraint that we have in the project. So basically any area above or to the right of the blue line, this corresponds to the beams that deflect beyond the line. So yeah, with the blue line, any area above or to the right of the blue line basically corresponds to the beams that deflect beyond the line. Then we have the green line here. The green contour outlines the feasible region where both of the constraints are satisfied. So all these values on the green line, this is what we want. All right, so basically for the contour plot, in conclusion, a larger height of H will reduce the stress, but it also increases the weight. A smaller width of B reduces the weight, but it increases deflection. And then the intersection of constraints determines the best combination of both, get the best of both worlds, basically.
So, yeah, that's a thorough explanation of both the code that we generated here as well as the contour plot. But we know that this script is successful because it optimizes the beam in 3 key ways. First way is it minimizes the weight, but even though it minimizes the weight, it also satisfies the stress and deflection constraints that we had in the problem statement. Then it also identifies the feasible region, that green line we had in the contour plot. And then it also provides a clear contour visual representative so that we can understand it. That is more or less the long and short of the project.